Yeah, hello everyone. I hope you can hear me. Could somebody confirm?
Yeah, we can hear you.
Thank you very much. So so today I will continue to teach about the electric field. But before I start to teach, I would like to remind you about that sample test, which I posted on Crowdmark. So please make sure that you have access to that sample test and that you submit solution. There is only one question, and solution is provided on lecture notes and tutorial notes. So remember, the purpose of the sample test is just to make sure that all of you know how to use Crowdmark. And in Physics 1801, I had a lot of trouble. Many students have trouble with Crowdmark. So I hope this does not happen again, because I had to spend tremendous amount of time to deal with all these situations when students could not get access to Crowdmark. So please make sure that you know how to use Crowdmark and submit the solution of that single question on test on that sample test by Thursday night. And I posted 2 messages about the sample test on eClass. So yeah, so today's lecture, as you remember, in previous lectures, we calculated the electric field produced by infinitely large charged plate. So we used 2 different ways to calculate the electric field due to infinitely large charged plate. We divided the plane into lines of charge, and then separately we divided the plane into many rings of charge. And for infinitely large plane of charge, the field is uniform. So imagine that that we have a very large plane of charge, then that field due to that very large plane of charge is uniform. And what you see on the screen, these parallel black lines represent a uniform electric field. A uniform means that electric field at every point in space have the same magnitude and the same direction. And as you remember, the electric field produced by a very large plate is independent of the distance from that plane of charge. So, so here we imagine that now we have now very, very large plate of charge. Let's say positive plate of charge is uniform electric field. And the magnitude of that field, as you remember, depends only on the surface charge density. But today I would like to explain a little bit about applications of uniform electric field. And in many applications, we need actually a strong uniform electric field. And one way to produce that uniform electric field is to use one single plane of charge. Although, as you know from Physics 1801, in practice, we use not just one plane of charge, but 2 parallel plane of charge, in particular 2 metal plate of charge, one positively charged, the other negatively charged. And then the region between these 2 plates, in that region, we have uniform electric field. I will be explaining about these 2 parallel metal plates probably next week. But for now, let us assume that this uniform electric field is produced by a single, very large plane of charge. So what are the applications? One important application is to accelerate charges. So imagine that we put a positive charge or a negative charge in that uniform electric field. If we release these 2 charges, then there will be a force acting. That force F acting on the charge will be equal, as you remember, Q times E. That's the magnitude of the force, Q times E. And if that positive charge will start to move in the direction of electric field, and of course will accelerate. So if all that arrangement would be in vacuum, so that there are no collisions of that charge with anything else, then the charge would accelerate and move along the straight line and gain very high speed. So we could accelerate charge to very high speeds. Or if you put negative charge into that uniform electric field, negative charge will move in opposite direction to electric field, right? Because if that plane of charge is positive, then positive charge here will be repelled by that positive plate, negative charge will be attracted by that negative plate. So yeah, positive charge and negative charge move in opposite directions and gain very high speed. So in terms of the magnitude of that acceleration, we can use Newton's law, which tells you that the force is equal mass times acceleration, where mass is the mass of that particle. Maybe that could be an electron, or this could be a proton. So that mass is that mass of electron or mass of the proton. And force, of course, acting then on that particle is Q times E. So by Newton's law, Q times E must be equal mass times acceleration, and acceleration is equal QE divided by M. And for example, if you substitute for Q charge of electron, magnitude, remember, electron is negatively charged, but I want to calculate just the magnitude of acceleration. So I substitute for Q just positive charge. And if electric field is about 1000 Newton, easy to obtain, and divide by mass of electron, which is very tiny, 9.11 10 to negative 31, then acceleration is enormous, of about 10 to 14 meters per second square. And we did this type of calculation in physics 1801. So this is just a review for you. Acceleration is enormous. And let's say that beam of electrons could be accelerated to very, very high speed. And for example, in particle accelerators, scientists accelerate beam of electrons or beam of protons in electric field to very high speed, almost approaching speed of light, and then study collisions of the particles. Or in another application, beam of electrons might be accelerated to irradiate cancer cells, a tumor. And in many hospitals, there are these electron accelerators because these electrons can destroy the cancer cells. So the beam of electrons or other particles, other ions are used in cancer therapies. Or another example might be in inkjet printers, where droplets of ink are charged and then accelerated in electric field. Or there are many other devices in which either ions or some particles are accelerated to very high speeds. So I don't want to spend too much time about this type of application because we did spend a lot of time about this in physics 1801. So somebody creates noise. So could you mute yourself? There is some kind of a background noise. So could you mute yourself, please? So any questions about what I'm explaining right now? Can you hear me still?
Yes, sir.
Yes.
Yeah, thank you very much. I don't know, somebody is creating that noise at the background. So that was all done in physics 1801, but the true objective of this lecture is actually to analyze what happens when we put an electric dipole in a uniform electric field. So this is the situation. So today's lecture will be actually about what happens when we have a dipole, electric dipole in a uniform electric field. And to just refresh your memory, electric dipole is just arrangement of two charges, one positive, one negative. And if they are separated by certain distance d, then this arrangement of two charges, one positive and a negative, is called an electric dipole. And it is convenient to define electric dipole moment. An electric dipole moment is actually defined as a vector quantity. Magnitude of that dipole moment is equal Q times D, where Q is the magnitude of one of these two charges. Remember, they are equal in magnitude, times the separation between these charges. So this is magnitude of the dipole moment, Q times D. And that R hat is the unit vector which shows the direction of the dipole moment, which we usually designate by letter P. And so letter P is the vector which is directed from negative to positive charge. Not from positive to negative, from negative to positive. This is the direction of the dipole moment. So the electric dipole moment is a vector quantity whose magnitude is Q times D and the direction from negative to positive charge. So many, as you probably know, many molecules are dipolar. The most important is water molecule, H2O. But there are hundreds or even thousands of molecules which are dipolar molecule. In terms of water, of course, water is made of oxygen, which is doubly negative, O negative 2, and 2 protons, which are positive, 2 protons. And as you know, this angle here is about 105 degrees. So that water molecule is asymmetric. And these 2 protons is like makes one side of the water molecule positive with the charge plus 2e, where E is the charge, elementary charge, right? Charge of the proton. And oxygen is negative, so this is negative 2e, negative 2e. And effectively, that negative charge and positive charge with protons are separated, right? Because that oxygen and proton are separated a little bit. The center of mass of oxygen and center of mass of these 2 protons are separated by tiny distance, maybe about 10 to negative 9 meters. And that's the dipole. Right? So what I'm trying to tell you that in most applications, these 2 charges of the dipole are called bound charges, bound because they are part of a molecule, and they cannot be separated from the molecule. So they are bound charges. And they are tiny, the molecules are separated by small distances. So these dipole moments are usually very small because separation D between these charges is very, very tiny. So many molecules have permanent dipole moment, like water molecule. But we will be also talking about so-called induced dipole moments, because when you put a molecule, which is not dipolar, or even an atom into electric field, so imagine that I put an atom. If this is the nucleus of an atom, in one direction and positive nucleus in opposite direction.
Professor,
yes, please.
Sorry to interrupt, but you cut out for a few seconds there.
Yeah, so it looks like I might have the same, although I was not notified about any instability of the internet. So hopefully that will be okay today.
Yeah, hopefully.
Yeah, I am getting actually a new modem from Bell on Tuesday, tomorrow, which is the most modern modem. So I hope it will help a little bit, but hopefully we'll survive today. So
hopefully it has more than one antenna. That helps always.
Yeah, so hopefully that new modem, actually the modem which I have right now is also the top of the line, but as I mentioned to you, I'm using that fiber optics, but for some reason there are some problems. So hopefully we will survive today. So what I was explaining is that yes, if you have a neutral atom, then center of mass of positive charge inside of the nucleus and center of mass of electrons is the same, right? Because electrons are all around the nucleus. So the atom has no dipole moment. But when you put it in electric field, then electrons are shifted a little bit relative to that positive nucleus, and that atom will acquire dipole moment. So any atom or any molecule located in electric field will acquire what we call induced dipole moment. So these dipole moments can be permanent, like in water molecule, or induced when you put a molecule or atoms in electric field. So we will be talking about these induced dipole moments a little bit more in the future when we analyze electrical properties of materials. For now, I just wanted to define or refresh your memory about electric dipole. That electric dipole we define as the vector quantity, right, of magnitude. That dipole moment quantity is magnitude is Q times D, direction from negative to positive. So any questions about the definition of the dipole moment? Well, if you don't have any questions, that hopefully everything is clear. Now, so imagine now that we put a dipole moment into a uniform electric field. So this is the dipole moment, plus q and negative q separated by certain distance d. And let's say that dipole makes certain angle here with the electric field, this angle theta with electric field. Now, of course, so there will be force acting on that positive charge in this direction. That force will be q times E, right? Charge times electric field. Positive charge force will be in the direction of electric field, but the negative charge of the dipole, the force will be in opposite direction of the same magnitude, q times E. In terms of magnitude, right, is the same, but opposite direction. So as you see, the net force on the dipole in a uniform electric field is equal to 0. So the dipole will not move to the left or to the right in a uniform electric field. But because the net force is 0, but the dipole will be rotated because these two forces, as you see, will try to rotate the dipole to make it parallel to the electric field. So dipole will rotate about that center of mass, about that center of the dipole, and the dipole will be rotated. So there will be a torque acting on the dipole. And I remember that I was explaining to you about the torque acting on the dipole in physics 1801, but here I repeat now this argument. Let us calculate the magnitude of that torque acting on the dipole located in a uniform electric field. So dipole will be rotated because the torque is not equal to 0. So look, what is the torque? Remember, the torque, which we designate by letter tau, is equal to magnitude of the force times the moment arm, which now I designate here by that symbol for now, r perpendicular, because that moment arm, this is called moment arm, is determined like this. First, you have to draw the line of action of the force. So let's say for that blue force acting on positive charge, line of action is the dotted line, right? It's the straight line which contains that vector F. That's the line of action of the force. And the moment arm is this distance, which is the shortest distance from that axis of rotation, which is through the center of the dipole, to that line of action. This is 90 degrees. So this is the moment arm. So this little thing is that what I called r perpendicular. And from this right angle triangle, you see the hypotenuse, this by 2, d divided by 2 from this triangle here. And then the magnitude of the torque, which is product F times moment arm, would be equal, F is equal Q times E, the force. And the moment arm is if this is angle theta, then moment arm would be actually equal to, actually now this angle, I designate angle theta. Let's say let's designate this angle theta. There's a little bit complication. So that moment arm, so I'm going to designate theta this angle actually for now. And the moment arm then would be equal hypotenuse, which is d over 2 times sine theta. This is a little bit now d2 sine theta, okay? So the torque due to one of these forces is, yes, QED over 2 sine theta, but the torque due to that force on the negative charge will be of the same magnitude. So you will have these two terms of the same magnitude, two torques, one torque due to that force F plus and the other F minus, and the total torque will be equal Q times D. D is the separation between charges. Remember, DE is not differential electric field here. DE is the distance, E is electric field sine theta, where that angle theta would be the angle between the dipole moment and electric field. So because that torque is written as QD E sine theta, and because Q times D is the magnitude of the dipole moment, which we called P, then the total torque acting on the dipole can be written as the cross product, because P is the vector, E is a vector quantity, and we have sine, angle. So this can be written as the cross product of the dipole moment vector cross electric field. And that's how you specify the torque as a vector quantity, P cross E. So remember, the cross product involves the sine angle between vectors P and E. So any questions so far?
I have a question.
Yes.
I'm just unsure how you got d over 2 sine theta.
Yeah, that's a very good question, because, you know, so I know what is really your question, and I try to address this in a minute. So what I designated, so this distance is the moment arm, right? That distance, so maybe I clean it for now because it's a little bit action of the force. And that moment arm is this distance from the center of the dipole to this must be 90 degrees, or I could use this triangle as well, of course. Okay, this triangle. Right? And this is the which I designated originally angle theta. Right? So this angle is actually this also angle theta. So I made a little mistake in previous explanation. So let us keep theta as indicated. So then this is the moment arm, this distance, or this distance, which are the same. You can use either this triangle or this triangle to calculate moment arm. So that moment arm is this distance, 1/2 d, because you see this hypotenuse of the triangle is half of d. D is, remember, d is distance from negative charge to positive charge. So this hypotenuse of the triangle is 1/2 d. And because the moment arm is opposite to theta, I have to use sine function, right? So to the moment arm, which is opposite to theta, I can get as hypotenuse 1/2 d sine theta. Did I answer your question?
Yes, you did. Thank you.
Yeah, welcome. And the total torque in terms of magnitude is equal Q d. D is separation between charges, E sine theta, right? Because here we have 1/2 plus 1/2 gives me 1. And the torque is normally written nicely, elegantly as the cross product, P cross E. Remember, P is a vector quantity. Moment dipole, electric moment dipole is vector quantity. So let us, so as you see, if the dipole makes certain angle with the electric field, then the torque will try to rotate the dipole to make it parallel to electric field. Because if the dipole is parallel to electric field, then the angle between vector P and E is 0, and sine of 0 is 0. So when the dipole is parallel, so if the dipole orientation is all like this, vector P, parallel, then the angle between electric field and vector P is 0, sine of 0 is 0. But if the dipole is anti-parallel to electric field, then the angle between dipole and electric field is 180 degrees, right? It would be 180 degrees then. But sine of 180 is also equal to 0. So as you see, when the dipole is parallel or anti-parallel to electric field, the torque is equal to 0. So the dipole will be rotated until the dipole is actually assuming this orientation, because parallel or anti-parallel, because then the torque is equal to 0. But as you will see in a minute, the energy of the dipole when it is parallel But for now, I wanted to explain about the torque, that the torque will be acting, the angle theta will be changing. When the torque is acting, the dipole will be rotated. Yes, please?
Yes, I'm sorry, you just got off for like 5 seconds, so.
Oh, you couldn't hear me for 5 seconds? Okay.
Yes.
We missed from like when you were talking about, so the torque is 0 for parallel or anti-parallel, but then you started talking about what happens to the energy, but we didn't hear what.
Okay, I repeat that. Again, I didn't get notification on my screen that no, there is interruption of internet. So I repeat that. So yes, so the torque is equal to 0 when the dipole is parallel or anti-parallel to electric field. But in terms of energy of the dipole, when the dipole moment is anti-parallel to electric field, is smaller than when the dipole is parallel to electric field. So the energy, when we start to consider energy in a minute, then you will see that the dipole actually likes that orientation when it is anti-parallel to electric field, because then the torque will be 0 and the energy will be minimum. Okay, so when the dipole is parallel to electric field, torque is 0, but that is not a stable situation, and usually the dipole will flip to the opposite orientation, as you will see on the next slide. But for now, I just explained a little bit about the torque. And another thing which I would like to add is that when the torque is acting on the dipole, the torque depends on that sine theta. So when the angle changes, when the dipole is rotated, the angle changes, which means that the magnitude of the torque changes as well. So during the rotation of the dipole, torque is not constant in magnitude. It depends on sine of the angle. When the angle decreases, the torque magnitude will decrease until when the dipole is parallel or anti-parallel, the torque will become 0. And the torque is maximum, of course, when the dipole is perpendicular. You see, when the dipole moment P is perpendicular to electric field, the angle between dipole moment and electric field is 90 degrees, and sine of 90 is 1, maximum value, right? So torque is maximum when dipole is perpendicular to electric field. So hopefully you did hear my explanations. So any questions?
I just have one quick question.
Yes.
Do we neglect the forces that the two charges exert on the other, on one another, because we treat them as bound charges?
That's a very good question, actually, very good. I'm glad that you asked this question, because I was talking only about the force exerted by the electric field on charges. But your comment is very important, that these two charges, of course, attract one another. And negative is attracted by positive, right? This is a Coulomb's law. So these two forces are in opposite direction. These are action-reaction forces. Now, because usually the dipole is part of the molecule, then these two action-reaction forces are part of the molecule, and they have no impact on the behavior of the dipole in external electric field. So forces are acting, but because they are part of the same molecule, they cancel each other because they apply to the same molecule, and they don't have any impact on the behavior of the dipole in external electric field. So very good comment. Thank you very much for your questions. Your questions are always very helpful.
Thank you.
Yeah, thank you very much. So good. Any additional questions? Yeah, so I then would like to explain now about the energy of the dipole located in a uniform electric field. And this is slightly more complicated to talk about energy of the dipole, but as you will see, the dipole in electric field has electric potential energy, and that amount of energy of the dipole depends on that angle theta between the dipole moment and electric field. And as you will see, we will derive the appropriate expressions. So depending on the orientation of the dipole, the energy of the dipole will be changing. Now, you should know from previous courses like Physics 1800 and Physics 1801 that the potential energy is not an absolute quantity, that we can only calculate the difference of potential energy, only the difference. That's why here I have written delta U. Delta means the difference of energy between two orientations, let's say of the dipole. In one orientation, another orientation, we will be only calculating always the difference of energy between two orientations, okay? And you should know from previous courses that the difference of potential energy is always calculated as the negative of the work done, in this case, work done by that electric torque, by the torque acting on the molecule. Now, and from physics 1800, and I hope that in physics 1800, not 1801, but in physics 1800, they explain to you that the work done by the torque is given by this integral torque d theta. Now we have to do integration if torque is changing. And I was just explaining to you that when the dipole is rotated in electric field, the torque do some integration. So for those of you who don't remember this concept from physics 1800, remember that the work done by the force, if the force is changing during the displacement, is calculated as F dx. If F now depends on displacement change, then you have to calculate work as integral F dx. But in this case, we have to calculate work done by the torque to rotate the thing. So instead of F, we substitute torque, and instead of X, we substitute angle theta. That's the analogy between that expression for work during the displacement and the work done during the rotation of the object. Okay, so when the object is rotated, we have to calculate work done by the torque, and that's the expression. Now, the meaning of the negative sign, I explain in a minute, but the negative sign must be there. Again, I have to rely at least a little bit what you have learned in physics 1800 and physics 1801, and these concepts were explained previously. So let us calculate what is the work done by that torque when it is rotating the dipole. So torque is equal PE sine theta, remember, cross product, PE sine theta, d theta, and I want to calculate work from initial orientation of the dipole. Let's say the dipole make initially angle theta naught until the final orientation theta. So P is constant, E is constant, uniform in space. So I can take P and E in front of the integral, and then integral of sine is actually negative cosine, right? So negative and this negative give me plus. And then I substitute upper limit cosine theta minus lower limit. So the total change of potential energy then is given as by this expression, PE cosine theta minus cosine initial. So any questions so far? Okay, so if you don't have any questions, then you should now, if the dipole is rotated such that initial, because the torque, remember, torque will be acting to reduce the angle. So if initial orientation of the dipole relative to electric field was given by this angle theta naught, then theta naught is larger than theta because the torque is rotated dipole to reduce the angle, which means that if theta naught is larger than theta, the final orientation, then as you know, cosine decreases with the angle. So this bracket will be negative. You see, this bracket will be negative because theta 0 is larger than theta. So I have to introduce negative sign here to account. Yeah, I hope you can hear me now. Can you hear me now?
Yep.
Yes, sir.
Yes, sir.
There was some interruption, so I had to start share the screen again. So I don't know, I did maybe something, I clicked on something, but anyway, so hopefully everything is correct now. So I was telling you that, yes, that that change of potential energy is given by this expression If we take that theta naught to be 90 degrees when that dipole moment is perpendicular, initially perpendicular to the electric field, then as you see, cosine of 90 is equal to 1. Cosine of 90 is equal to 0, I should say, 0. So cosine of 90 is of course equal to 0. So then under that assumption that if that initial orientation is 90 degrees, and for that initial orientation, cosine of 90 is 0, then the change of potential energy would be just equal negative PE cosine theta, where theta is that final orientation of the dipole relative to electric field. So then that change of potential energy, and remember, so that would be the change of potential energy of the dipole relative to the orientation when the dipole was initially perpendicular to electric field. So that perpendicular orientation of the dipole will be our reference energy. So we will assume that now that energy of the dipole when it's perpendicular is equal to 0. So that will be like 0 reference energy. So under this assumption, then the change of potential energy when the dipole is rotated from that initial orientation when it's perpendicular to new orientation, that change of potential energy can be written as negative PE cosine theta. Because P is a vector, E is a vector quantity, I can write this expression as the dot product. So that change of potential energy can be written as negative P dot E. And remember that dot product is commutative, so we can change the order of these two vectors, but normally it is written P dot E. So that is how you calculate the change of potential energy using this expression. And remember, again, I repeat again, that this expression is only valid if we take that initial orientation to be 90 degrees, that dipole is perpendicular to electric field. So one additional change is that instead of always writing delta U, and that delta signifies the difference of potential energy between two orientations, that the delta is normally dropped to avoid writing it again and again, and we write that energy of the dipole just using symbol U. That energy of the dipole in electric field is just written as negative PE, P dot E. But remember, I repeat for the 5th time, that this expression is really energy of the dipole relative to the energy of the dipole when it is perpendicular to electric field, and that energy of the dipole perpendicular to electric field is equal to 0, according to this expression, right? Because cosine of 90 is 0. So that's why in all books that potential energy of the dipole in electric field is written as negative P dot E. But remember, this is still the difference of electric potential energy of the dipole, but the difference relative to this orientation of the dipole when it's perpendicular to electric field. So these are little complications, but now I have to explain this properly because I want you to understand everything. So remember again and again that potential energy, we always calculate the difference of potential energy of any type, whether gravitational potential energy. When you calculate gravitational potential energy, you calculate that mgh relative to maybe level of the floor or level of the table, always relative to certain reference level. In terms of the dipole moment, we calculate that the reference level is when the dipole is perpendicular to electric field. That's the reference energy, right? Because when dipole is perpendicular to it, cosine of 90 is 0. So that's our reference level. And then that energy, using this expression, we always calculate relative to that 0 energy when the dipole is perpendicular to it. So I'm pretty sure that now you have many questions. So yeah, please unmute yourself and ask questions.
I have a question.
Sure.
I was just wondering if you could explain one more time why you changed the sign from positive to negative in the middle here.
Very good question. Yeah, I explained that too quickly because, when the torque, remember torque acting on the dipole is equal dipole moment, P times electric field sine of the angle. right? So when the dipole, when the torque is acting, that angle theta is decreasing because the torque is trying to align the dipole to be parallel or anti-parallel to electric field. So this angle theta decreases. So when you look here, I integrated from initial angle theta naught to final angle theta. So theta 0 is larger than here. You see, theta 0 is larger than final orientation theta. And because the cosine, you know, when you plot cosine function, so here's the value of cosine function. Cosine function is something like this, remember? So you see when the angle decreases, value of cosine, value of cosine as the function of theta, you see this is cosine function, part of cosine function, the value of cosine function decreases, which means that if theta 0 is larger than theta, then this cosine theta 0 is larger than cosine theta, and this bracket is negative. And I have to take this into account by taking this negative sign, including this negative sign here. That's the reason, because this angle theta under the action of the torque will be decreasing. And that's the meaning of this negative sign, that in this expression for potential energy, this negative sign must be there, because only then that energy of the dipole calculated relative to that perpendicular orientation will be all correct. So this negative sign should never be missed. So I hope I did answer your question. And the answer to your question, short answer was that because the torque is trying to reduce the angle to align the dipole with electric field.
So
Okay, thank you. It's just like, because it just kind of appeared out of nowhere, so.
Yeah,
I
I know. It appeared a little bit. I added it because of this.
Okay,
Yeah.
Because sorry, like I thought just having cos theta minus cos theta 0 would already give us the negative. So it like, are we like
Yeah.
showing like the change in the angle by adding the minus?
Yeah, this is a good comment as well, because you know, if we would have specific values, then yes, that theta would have to be smaller than theta 0, and this would, that sign would come from here. But I included it just taking this into account right away, because otherwise, no, as I'm saying, we would not get this negative sign. So this is a little bit, I understand your question. I just, with specific values, you see, like you are commenting, this negative sign would come from here, but I included this explicitly. Why I did it? Because when using this expression here, we always calculate energy relative to when theta 0 is equal to 0. So you see this, that cosine of 90 is equal to 0, I already take it right away, that any energy will be calculated relative to that perpendicular orientation. And then the negative sign must be there, as you will see from the next slide. So your comments are all very good, and I understand your questions very well, that it's kind of a little bit like sort of almost artificial taking negative sign twice, because if, you know, if theta 0 is larger than theta, then negative sign could come. But I want to include this explicitly, because that theta 0 would be 90, always 90, and cosine of 90 is 0. You see?
So like, I'm sorry. So like the final answer will be a positive number, right?
Yeah, opposite number. Yeah, because we take that cosine of theta naught as 0 degrees. Yeah, for theta. So that's the reason why it looks like manipulation, but it is not really manipulation, because. But the true answer to your questions, to these last two students, is that we take really that reference energy, because whenever you calculate potential energy, we calculate it relative to certain reference orientation or reference level. And we are taking here that reference level when the dipole is perpendicular to the electric field. And then cosine of 90 is 0. So that will be our reference level 0. And for that reason, I included that negative sign explicitly, that cosine of theta will be less than 0 if no. So that's the explanation. But very good questions, and I understand your question very well. But the key point is that this expression, which is correct expression, is the energy of the dipole, but only relative to that orientation when the dipole is perpendicular, when its energy is equal to 0. Then this negative sign has the meaning, as you will see on the next slide. So maybe before I'm talking too much, because you asked good questions, but I'm talking too much, I prefer to now interpret maybe this expression so that you have really good understanding of the meaning of this expression. So let us go to the next slide. And in the next slide, you see, let us use that expression negative PE, P dot E, and calculate what is the energy of that dipole for 3 important orientations. So first, let us say what that expression gives me when the dipole is perpendicular to the electric field. So if theta is 90, then of course, dot product P dot E is equal PE cosine theta, with that, including that negative sign. Remember, that negative sign must be there. And then of course, cosine of 90 is 0. So the dipole energy for that perpendicular orientation, according to this expression, is equal to 0, as expected. Now, what about when the dipole is anti-parallel to electric field, you see? So this anti-parallel, which means that the angle theta is 180 degrees. Well, then this expression will give me negative PE cosine of 180. Cosine of 180 is negative 1, and this negative gives me plus. So the dipole, energy of the dipole, when it is anti-parallel, will be P times E. Will be P times E, plus P times E. And I now realize I was making a mistake in some of my previous explanations. So that will be dipole energy. But when the dipole is parallel to electric field, which I don't have the graphic for that, but if electric dipole is parallel to electric field, then the angle is equal to 0. And then the dipole energy will be PE cosine of 0. Cosine of 0 is 1, and energy will be negative P times E. So as you see, according to this expression, the lowest energy, and I apologize for mistake in my previous slides, the lowest energy, of course, of the dipole is when it is not anti-parallel, but parallel. I have no idea what came to my mind to say that energy was minimum when it's anti-parallel. As you see, energy of the dipole is minimum when the dipole is parallel to electric field. So when you plot the energy of the dipole as a function of that angle theta, then when the dipole when the angle is 90 degrees, the energy is 0. When the angle is 0, the energy is negative P times E, and the energy changes like according to cosine function or like this. And when the angle is, so I'm sorry, I made mistake. Sorry, I didn't sleep well today. So yeah, I plotted again. Sorry. So potential energy as a function of angle theta. When the angle theta is equal to 0, then energy is equal to 0. But when the angle is 90 degrees, when the angle, no, sorry, it was correct actually. When the angle is 90, the energy is 0. When the angle is 0 is negative. So yeah, that was all correct. Sorry. All like this. So this is the part of cosine function. You see, like this is part of cosine function, negative cosine function. And so this energy, when cosine angle is 0, is negative P times E. When the angle is 90, energy is 0. When the angle is 180 degrees, energy is equal P times E, plus P times E. Yeah, so energy changes in sinusoidal way, and the minimum energy is here negative P times E. That's the lowest energy. Why it's negative? Usually students ask why it's negative. Well, because we calculate energy relative to that 0 energy, right? When the angle is 90 degrees. So when dipole is parallel to electric field, energy is less than 0, so it's negative. Okay, so that's the meaning of this expression of the potential energy of the dipole, negative P dot E. The negative sign must be there. Any questions so far? So I'm sorry for my little mistakes on previous slides.
I have a question about like the dipole energy, because from the previous slide we said, like, we had the expression where we had the difference in the cosine angles from like theta, like cos theta minus cos theta naught.
Yes.
But because we say that we're like taking theta naught to be 90 degrees as the reference angle, then we have that expression. But then on the second slide, like the expression negative PE cos theta.
Yes.
But then on the second page, with the using the formula of the energy or the expression that we derived for the U dipole is equal to P E cos theta, then at that, like, how would have there, like, there was no movement then? Because if we said theta naught was 90, but now we're saying theta is also 90, then there was no torque.
Yeah, well, the torque would be acting, right? So the torque would be acting, but energy. So when the dipole is perpendicular to electric field, of course, torque will be maximum. And the torque will be trying to rotate the dipole to make it parallel to electric field, where energy is equal to 0. Or minimum, I should, not 0, but minimum, right? But in terms of energy, so torque would be trying to rotate the dipole from that perpendicular orientation to align the dipole with electric field. But in terms of energy, remember that potential energy is not an absolute quantity. We can only calculate the difference of potential energy between two orientations. Only the difference is meaningful. You cannot measure, or we should not even talk about energy of the dipole at one orientation. Because, you know, when you use, I answered your question in a minute, and I still remember your question. You see, because when you write the expression like this, you might have impression that this is energy of the dipole at particular orientation. But I'm telling you that we can only calculate or measure only the difference of potential energy. This is the significant thing, only the difference of any type of potential energy. So remember, when, for example, in gravitational potential energy, when you write mgh, quite often you might have impression, well, this is just energy when mass m is at height h above certain reference level. But this is really the difference of potential energy between, let's say, this height and relative to the ground, where this is h. So any type of potential energy, whether electric energy or gravitational energy, we only can calculate the difference of potential energy. But when we calculate the difference, it's convenient to calculate the difference relative to certain convenient reference level. So when you use mgh, usually this is relative to, let's say, the floor level. But when we calculate energy of the dipole, then it is convenient to calculate energy relative to the orientation of the dipole when it is perpendicular to electric field. So when I write this expression, U equal negative PE, this is really energy of the dipole, but relative to that, to the energy when dipole is perpendicular to it. And that energy when the dipole is perpendicular to it, according to this expression, is 0. So that's the convenient, you see, reference level. That like energy of the dipole when it's perpendicular, according to this expression, is 0. That's our reference level, reference orientation. So this expression is very convenient, and of course always used in all books. It's extremely important, actually, expression, but it leads to some misunderstandings. It can be, first misunderstanding is that students have impression that potential energy can be calculated at certain energy for certain orientation, but I repeat again that this is really the difference of energy between orientation when it's perpendicular and when it makes angle theta. Right? So that's one important clarification. And this negative sign is there because, again, because we take that convenient reference orientation of the dipole to be perpendicular. So that's why this negative sign actually occurs in that expression. And the meaning of the negative sign is that that for some orientation of the dipole, again, relative to that perpendicular orientation, for some orientations, let's say like this orientation, or when it is antiparallel, when the dipole P is antiparallel, energy is negative. But when the orientation of the dipole is making angle less than 90, or when it's parallel, then the energy becomes actually negative. Here it becomes negative, and for these two orientation becomes positive, right? Depending on the value of the angle. So that's the key point, I think, to understand how to interpret that expression negative P dot E. That this is really the difference of energy relative to that perpendicular orientation of the dipole, and energy then can be negative or positive, right? Depending how that cosine of the angle is. Remember, cosine of the angle can be plus or minus, and including this minus that gives you plus or minus of energy. So that's what it is. I'm talking quite a lot. I hope I did answer in the end your question, but.
Yeah, I was just like, it's more just like I guess like clarification, just because if that if that expression was derived with the assumption that with the reference of theta naught is equal to 90, then we're setting theta equal to 90, then the change in energy is 0.
Yeah, it's 0 because it's still relative to the same orientation, right? So.
Right, yeah. Right. But I was just like, kind of like, why would you have to, like, is it just more like just for showing us the, like, as an example? Because I just didn't understand the significance of like why you would want to calculate the potential energy relative to the same reference point.
Yeah, only to show you that this expression actually works.
Oh, okay.
This expression, how to apply this expression, and that this expression really works. And that's physicists and engineers are writing that energy of the dipole in that convenient way. Remember, this is convenient way to write it as the dot product. It's very elegant, and now we know the meaning of the dot product. But I hope that all of you now understand that, yes, that potential energy we calculate relative using this expression relative to that perpendicular orientation where the energy is 0. And when you use this expression, PE cosine 90 gives you 0. So that's how it is. But why energy sometimes is positive and negative, that is because depending on the angle of the dipole for this orientation, or even now when dipole is antiparallel to electric field, now cosine of 180 is -1, so energy will be positive. But when the dipole is parallel to electric field, energy then will be negative because of this negative sign, the less than 0, negative. So I wanted to clarify that yeah, energy is positive and negative, can be positive or negative, because our reference energy is that 0 energy when the dipole is perpendicular to it. So it's nothing complicated. You just have to accept that's the meaning of this expression, that this is the potential energy difference relative to that perpendicular orientation. So it's nothing complicated, but these expressions, for energy negative P dot E and for the torque, P cross E, these are now pretty crucial expressions, because there are so many applications of the behavior of the dipole in electric field, because now properties of many materials, and materials have many different applications, different materials have many different applications in engineering, then we have to deal with these dipoles when we analyze properties of these materials. And that will be the most clear when we talk about, for example, capacitance, when we will have to consider the dipoles of the material located in electric field. So that's how it is. And I was planning to give one example, one specific example, which is on the next slide, on this slide. It's a very simple example, but because time is now running short, the lecture is almost finished, I will do this example in tutorials on Wednesday. Again, this example, I'm sure if you read this slide on your own, you will understand what it is, how to solve it. But still, I will do it on in tutorial on Wednesday. And of course, there will be some questions about the dipoles in electric field on the coming test in about 2 weeks. So at this point, I finish, and I sorry that I made a couple of mistakes. I didn't sleep well tonight, so I'm tired, but I will now finish and stop recording.